With that, I think I would like to invite our uh, first speaker for this session, Mr. Octavio from Nova Smar, who will be speaking on software-defined application in Opus architectures. Over to you.
Hello, hello. Thank you. You have the, yeah, it's working. You listen me well? Okay, okay, very good. Okay, good. So, good morning, everybody. So, first of all, I'd like to do an acknowledgement here from RC. First, to be a supporter of Opus technology. So we are seeing that this technology world is migrating to AI, but we still have some kind of OT things to solve. So thank you very much, ARC, especially here in India for this event. Second, it's really nice to be here back. You see a lot of known faces for last year. So I'm coming to India consistently since last year. So I think it's the first time that I come to India, and I think I know more cities here in India than in Brazil because I'm traveling a lot here. So it's very good to be here again and see many of you back. Third, my name is Octávio Paschoal. I work by Smar, a Brazilian company. Please don't talk about World Cup with me because I'm still very upset. If there is somebody here from Norway, please leave. I don't want to talk with you. And the topic of my presentation today is about Opus applications. So software-defined application in Opus architectures. I promise you that there is not going to be any gold and blue diagram this time, okay? Because I think you know very well about it. So good. What are the topics of the presentation? First of all, Opus as software-defined applications ecosystem. I'm going to talk a little bit about some structures in Opus architecture. Two, actual industrial Opus application. What you have seen, we are seeing in some of applications that you are having end users. The third part, a specific software-defined application for Opus, which is the main part of the presentation, which will be the Opus Flow Computer and any user-defined function block. Then we finish with the roadmap and then conclusion. So it's like a research presentation here, right? Good. First, let's start here. So Opus as a software-defined application ecosystem. What Opus says, one very resumed phrase, sentence, hardware and software decoupling. So one of the premises of Opus is to have this decoupling so you can have freedom to develop applications and you can have freedom to build your automation architecture with that. But what Opus defines actually are the interfaces. So I brought to you here a part of the, a print of the part one of the Opus standard, which says that Opus standard defines the interfaces. The functionality required by the interface is defined, but how each component provides the functionality required by interface is not defined. It's left up to designer. What it means? To have an Opus component, you must define the interface, which be connected to the other components, right? What is inside our application is up to you. So if you go for an analog input block for a control system application, you know what analog input of a control system does. But what is programmed here inside is up to the designer. If you want to embed new capabilities, it's up to you. The interface should be well defined. So, again, about interfaces. Sorry. Here we have some other block diagram from the standard. And this block diagram shows, it is not working these things, shows some components of an Opus application. Your Opus application can have all of those blocks or part of them, depending on how you are working with the Opus application. But you can see that you have these connections here. And such connections are these interfaces. So, talk about communication. One thing that you must have that the Opus, you need to have the Opus signal, which is OPC based information model with some features, some information, and your blocks should talk, should have this information to receive this OPA signal. So these interfaces are defined by the OPAs. And here I have in your left side what comes from the standard. On your right side, what in this Smar you have developed. So you have, for example, in Nova CSB, which is the configuration tool, is in the same part there in the editing tools, and you have the interface, for example, import export, which will be responsible to generate the AML file that's going to become for the portability. So these interfaces are very important. Another part of interfaces, also from the standard. Everything that is red here is defined in the standard, which are the interfaces. Something which is black is not defined. So part of your component is up to the designer, is not on the standard. The message here is that you have interface, you can do whenever you want. Good. And what you have now for industrial OPAS applications? So normally we have function blocks libraries for legacy systems to build your strategy. So what was done on the beginning of OPAS? And remembering that very famous scene of Titanic movie, it was 82 years ago. So a long time since we started OPAS, we had the compatibility OPAS for legacy applications. So we took all the function blocks for legacy systems and you defined it to be used in OPAS applications defined these standards. So having here the function blocks, right? It is generated the XML, node set, and the source code, which are necessary to be deployed in an OPAS architecture. So with that, what you find normally nowadays in OPAS applications in end users that are investing on it? Process control. So you can have here example, interfaces like inputs and outputs. You have interfaces between different components, right? Running function blocks to have, for example, AI, PID, and analog output. On your right side, we have like a configuration tool doing the same thing. Okay? So this is what we have now, right? This is what we find, and this is how we do our demonstrations, what we expect that the end users at least use this kind of thing in applications. But, again, being OPAS, an open architecture that defines the interfaces and what runs inside the application is up to you, not to explore more. Why not to explore more? So, specific software-defined applications. The first one that I would like to bring to you, flow computer. A lot of people here come from oil and gas applications, right? Please raise the hands. Yeah, good, very good. So you know what a flow computer is. So flow computer, use it for physical matter in custody transfer. This means that deals with a high aggregate value exchange. I'm extracting natural gas. Natural gas will be used for a lot of things. This is money. And when you think about physical matter and custody transfer, this money change hands. And if money change hands, accuracy matters a lot, right? So use flow computer for that. And flow computers, what they have specialized and standardized algorithms by ISO, API, AGA. So the accuracy should be very high according to the conditions that you have for your exploration. So you can understand the flow computers as standalone specialized automation system. It's there, it's automated, it receives I/O, it has processing. You put an HMI. So this is an automation system, but not a standard automation system to run PIDs, right? So another feature of flow computers, low scalability level. You have one flow stream, you have one flow computer. You have 1,000 flow streams, you have 1,000 flow computers. So you cannot just put, or the most part of the flow computers, you cannot just put I/O cards like you do in a traditional DCS. You need to have a new flow computer for new applications. So that's why low scalability level. And what you have, then we have like a chain effect. High aggregated value product, it means that the product will have higher cost because you are dealing with a lot of money. And if you have low scalability level, the solution cost is proportional to your string quantity. So it becomes very expensive. Of course, on the end, you expect that your operation will you recover this investment. But it's something that you must have in hand. Then you have, on the other hand, Opus architecture is known for higher scalability level, right? You have DCNs with high capacity to run your applications. Running in containers, and you know that containerizer, the software is easy to replicate. I have one block there, and just copy and paste, more or less like this. And Opus defines the interface, not the algorithm. So why not have this idea? Develop a flow computer algorithm, a software-defined application in Opus architecture. Because it's algorithm, you put in a container, you can put in a DCN, you can start to scale it. So what was the idea? We had a POC with an end user, right? A POC for oil flow measurement in a skid. And how you validated that? There is one certified flow computer manufactured by Smar, certified in Brazil and Europe for physical metering. So we expect high accuracy on this flow computer. We put both solutions in parallel, to run in parallel. So we had this validation. We put the same IOs for them, dividing a simulation in the first time, in the first hand, and you put the calculations then to be compared because you have the reports there. So what we get? We got the comparison instant calculated flow because depending of the process condition, you need to calculate the corrector factors on that time, and then correcting these factors during time, you have the totalization at the end of the hour, or the end of the day, or the end of the month. So it's used to have the correct information of your flow measurement during this time. So what you got as result? 100% correct instant flow and correction factors, and long-term totalization error about 0.0025% in simulation using that. And here we have the function block of the flow computer receiving the data for pressure, density, temperature, and pulse. And here you have the simulation. On this part here, you have our standard flow computer. So you can see highlighted some information, the indicated value, the gross volume, the net volume, and the mass. And here I have a view of our UI expert reading the data from our Opus flow computer. You can see there is the same. This is the instant, not the totalization. The totalization comes integrating these values. So this is what the result that you got. So this is the first software-defined application that I'd like to show you. The second is the user-defined function block. So here you have a sentence. Okay, in Opus market, there are vendor runtimes, engines, and function block libraries. But what if I want to have some freedom to develop my function block? Right? How to explore flexible structure? Because one thing is to go to a runtime or a configuration tool and have access to function block library and use it in my strategies. But what if I want to do something by myself? There are a lot of individual initiatives. I can say, for example, Mr. Sunil from NTPC, he's doing a very nice job in Raipur, building open architecture systems, but probably not yet defined according to Opus, to standard Opus. I have seen also this in Netherlands. People do a very nice job, but not related to Opus, individual ones. So if I want to have something according to the Opus standard that give me freedom to do it. So why not develop an integrated tool where an application can be created from standard language, interfaces are defined, and created an Opus compliant block. That's why UDFB comes from user-defined function block. So, what is the user-defined function block? We started with structured test language code, so you program whatever you want. Doesn't matter if you want to build a new PID block or if you want to do like a interlocking application. for motor start or whatever. So we have the Opus time definition variables mapping, which will be the interface, and you generate this node set. This node set is the file that is going to be imported inside the DCN as the function block. So we create your function block from a code that you can create, right? And even this first study was published in, I think, Elsevier magazine. So we have the link there, you can check it. And some pictures of that. This is a general view of function block. What you have inside, again, is up to the designer. You define the interfaces, function block inputs, function block outputs, and you can also define some monitoring variables. You don't want to have it as input and output, and just want to have as monitoring. You can have this also. And here we have the structure, the Nova FFB, function block builder. So on this, we have a library blocks there, the block manager. You can come here, you can have your structure test, right? Defining the variables, the type of variables from your code. Here, you can define the type of the variables, the interfaces, and here you add the data. So here you put on your information model what is going to be your variable that you're going to be used in OPC way, right? Good. Finishing. What's the roadmap about these applications now? For flow computer, first finish flow computer validation real stream. You have already performed it. We found some gaps, not in Opus, but in other parts of the integration. Right? This is the first part. Develop function blocks for gas, flow, metering, and proving, because we implemented algorithms for oil, so we can do it for gas and for proving as well. And one of the biggest challenge is the flow computer function block certification. Because of this, you have local regulations. We have a local regulation in Brazil, we have local regulation in India. So this is something that needs to be defined actually, because even the architecture is something different that normally we have for flow computers, right? For UDFB, implementation large scale, right? Proof of concept with OPAF end user members. Now we have internally and with some universities testing it, and release both solutions commercially, knowing that this function block builder should be a tool free of cost, so everybody can use it to build your Opus application or Opus function block with whatever you want to have inside. Conclusions. Opus enables any developer to create own solution, not locked in architecture. This is something that's been spoken since the beginning of the Opus, that Opus should be like the Android of automation, and you can have like a Google App Store, Opus App Store that I remember when the first presentation about Opus, engineer from Petrobras said that maybe an Indian genius, 12 years old genius guy will develop a function block in India, put it on the marketplace, and anybody in the world could use it in Opus. And I remember that he said, the Indian genius guy. Really nice that. So why not? This is something that the Opus environment bring. You can have just solution designers, and you can use it for any applications. Second, interface definition make possible any algorithm development in Opus. That's it. You define the interface and you create anything. Not only process control shall be explored. Process control is the beginning. It came from process for process control applications, but we can explore it. And last but not least, and actually the most important part, any user must participate in to bring ideas and as co-authors of the solutions. The flow computer comes from an end user, this idea, right? Why not come example, rotary machine, turbine, I don't know, right? Any specific application that you have for a certain process in your facilities can be brought as an idea to be implemented. Okay, if you want to check more, we have a booth here. We are running the 3 applications there. a standard control loop, UDFB, which is configured a motor starter, and you have a flow computer running with simulation there. So I can show to you. So that's it, my message for today. It's something that I think should be a little bit different from Opus. I'd like to thank you very much for attention. You can contact me if you want. I'll be here in the exhibition. So thank you very much.